For the third talk of this session, we have Yijia Xu, and he's going to talk about encoded quantum gates by geometric rotation on tessellations.
Thank you. First, I would like to thank all the organizers for giving me a chance to share our work here. I'm Yijia Xu, a PhD student at University of Maryland, and this work is in collaboration with Yixu, Wang, and Zi-Wen. They are from Tsinghua IAS and the Yao Center at Tsinghua University. Unfortunately, Yixu was supposed to be in here, but he failed to get his US visa. So since here's QIP, I agree I believe everyone agree with the significance of quantum error correction because it is a crucial technique to realize quantum computing. And generally, a quantum error correcting code is defined by an encoding map E that maps our logical Hilbert space to a code word, a logical state in the logical Hilbert space to a code word in physical Hilbert space. And those code words are entangled, and the entangled structure help us protect the encoded quantum information from the noise of the environment. However, the entangled nature of the code word also makes it difficult to perform logical gates in general. And in the past few decades, most of the efforts is to design quantum error correcting code with a versatile set of easily implementable logical gates. And due to the distinct nature of different physical platforms, different notions of easily implementable logical gates are proposed. Like in the DB setting, we typically talk about transversal gates. And in the bosonic oscillator case, we typically refer that Gaussian unitaries are easy to implement. To address this problem, a concept called G-covariant encoding is proposed to design quantum code with certain logical gates can be easily implemented. The basic idea is shown in equation 1. We have an encoding map E and a logical state K acted by a group element H in the logical group G. And if a logical state with logical action rho L of H can be realized by a physical action rho of H acted on the encoded states E of K, we call this code is G covariant. Means all the logical group elements in the group G can be realized by implementing the physical representation of the group G. And in this work, we constructed and investigate the quantum error correcting code whose logical action rho L can be implemented by physical geometric rotation rho. The key idea is based on the similarity of logical and rotation group structures revealed by their group presentations. And the footnotes are the previous work on a G-covariant encoding from various different perspectives. Yeah. So here's a formal definition of the group presentation for various commonly used group. The first one is the qubit poly group. We have two generators, X and Z, and they satisfy certain relation, means x squared equal to z squared equal to xz together power to the fourth gives us identity. And similar for qubit poly group, we have two generators, and if we take x power to d or z power to d, we should have identity, as well as that omega should be the central element of this group, which corresponds to the last two terms of the equation 3. The omega is the group commutator between poly x and z. Also, the single cubic Clifford group can be written in a similar manner. And there are various different choices of the generator of the single cubic Clifford group. Here we pick a special choice from the reference from Dennis and Varia. And we have two generators S and U, and they also satisfy for certain relation, means that certain products of those generators gives us identity. Even the universal gate set for single qubit gate can be written in this form. We have two generators, H and T, and they have certain relation, although those relations are a bit more complicated than previous group. But all the examples above have two generators with finite orders. And those structure motivates us to consider a symmetry group based on from 2D tessellation. And the 2D tessellation group basically is the symmetry group of regular triangle tessellation on a 2D space. Here I use example in the Euclidean space. And this is called 244 tessellation. And each tessellation is uniquely specified by 3 positive integers. So the symmetry group of this tiling is generated by refraction along 3 different edges, small a, b, and c. And if we combine 2 neighbors refraction, we will get rotation around the vertex A, capital A, B, and C. We label them by RA, RB, and RC. And the rotation RA, RB, and RC means that rotate around certain axis by 2 pi over the corresponding integer. So the formal, we can also see that the triangle group delta PQR can be written as equation 7, where we have 3 generators. They are refraction along 3 different edges with certain relations. If we reflect along the same axis, the same edges twice, we will have identity. And if we rotate around certain axis by 2 pi over p times, we should also have identity, and similar for the last 2 terms. And here we're interested in the orientation preserving operations. So it is described by a subgroup of the triangle group called proper triangle group, delta bar. And it is the index 2 subgroup of the triangle group. And it has 2 generators, I and RB, and they are rotation along axis A, B, or B by 2 pi over P or 2 pi over Q. And also the RC, notably that RC can be generated by I and RB. So the presentation of the proper triangle group is written in terms of equation 9. We have 2 generators, I and RB, and this proper triangle group also has certain relation, identity relation. And moreover, actually, the different choices of 3 integers, p, q, and r, also reflect a certain geometry property of the surface that we are going to tessellate. If we're summing over 1 over p, q, and r, if this summation is greater than 1, the tessellation can only be realized in sphere. If the summation gives us exactly 1, this tessellation is allowed in Euclidean plane. If it is smaller than 1, the tessellation can only be realized in hyperbolic plane. So basically, as I have shown, that the proper triangle group is pretty similar to the logical group we are interested in. However, they are still not the same. Main difference is that those logical group we interested in, for example, the Clifford group or the universal gauge sets, has more relations in their group presentation. That means we need to impose certain relation R to the proper triangle group, such that we can realize the logical operator in G by implementing the operators in the proper triangle group. So algebraically, adding those extra relation means that we quotient the proper triangle group by the normal closure of those extra relation. The normal closure means the smallest normal subgroup that involve R. So we aim to construct the relation, the fourth point, where G is equal to proper triangle group quotient out the normal closure of R. So geometrically, R identifies different points on a surface and defines the unit cell of our code word. Our code word will be certain, superposition of points following certain tessellation pattern. And from a QEC perspective, we call R as our generalized stabilizers, something similar to the stabilizer of GKP codes. So overall, the logical operators in our codes means the logical operations in G should be implemented by spatial rotation in a proper triangle group. So once we talk about the operation, let's see how does the code word look like. And there's a general encoding formalism proposed by Dennis and Leverrier. Let's say we have two distinct Hilbert space, a logical space and a physical space. And we have a logical presentation, say rho L, and rho to be a physical representation that they are acting on different Hilbert space. And we can define then a linear operator called V, which is a tensor product of the logical representation and the physical representation. It's also called group representation interliner. And then we can choose two states, which is sigma, called reference state in the logical Hilbert space, and cat init, which is an initial state in the physical Hilbert space. And the code word k bar in the physical Hilbert space can be written as equations 11, which is a superposition of initial states acted by different physical representation, rho of G, and we're summing over all the G in small g in a logical group capital G with coefficients which represents this sandwich. And actually, the initial states can be an arbitrary state in the physical space, but choosing different initial state will yield different codes with different constructions, but the same logical group. So here is an example, a simple example that realizes Pauli's. And the code word, our code words are tessellation, means the superposition of points, which is superposing a row of G acting on initial states with coefficients, which is the sandwich, and we're summing over all the small g in the quotient group. Yeah. So the figure on the left-hand side depicted how does the code word look like. We have logical 0 and logical 1. The logical 0 are superposition of red points with +1 coefficient and pink points with -1 coefficient. The logical 1 is a superposition of blue points with +1 coefficient and light blue points with -1 coefficient. And I also labeled 3 rotation axes and with their logical action. For example, if we rotate the x-axis by 180 degrees, we are permuting the red and blue color as well as light blue and pink color. Means that we are permuting the components between 0 and 1. So we can see it is indeed a logical X. And for the logical Z, we are permuting blue and light blue, while the red and pink remains unchanged. So that will, the logical 1 state will pick up a -1 sign. So that means it is a logical Z gate. And if we rotate around the XZ axis by 100, by 90, rotate around the XZ axis, we are performing cyclic rotation, cyclic permutation between those 4 colors, and it can be easily checked that it implements logical XZ gate. And also, in the Euclidean plane, we can do similar. We can talk a similar story that we have. The figure on the left-hand side depicted how the unit cell of our code word. The logical 0 state is a superposition of red point with +1 sign and the pink point with -1 sign. And the blue and light blue points superpose the logical 1 state with coefficients +1 and -1. And if we rotate around 3 different axes, we can easily verify they implement corresponding logical action. But since we are done with the Pauli gates, so how can we say it about like Clifford or more complicated gate sets that realized by rotations? And that due to the structure of the Clifford single cubic Clifford gates, that we have to move to the tessellation in the hyperbolic plane. So here is code word. How does the code word looks like that allows single cubic Cliffords realized by geometric rotation in the hyperbolic plane? The central rotation axis denotes the rotation axis to implement logical S gates, which has 8-fold rotation symmetry. And the rotation axis I pointing here denotes the rotation axis that's to implement logical U-gate, which has 6-fold rotation symmetry. And the code word, this is the code word looks. This is how does the code word looks like for logical 0, which is the superposition of all the red points with a coefficient adjacent to each point. And the solid line encloses the unit cell of the code word. So here is the logical 1 code word for list Clifford code, which is a superposition of all the blue points with the coefficients, the neighboring coefficients. So aside from previous example, actually we can, based on different logical group we are interested in, we can construct different kinds of codes, realize certain logical group by geometric rotation. For example, we can those are examples we demonstrate in our paper. We have qubit or qubit polys, also the qubit Clifford, and also the binary icosahedral, which includes even gates outside of the Clifford hierarchy. And there will be another talk about codes that can realize binary icosahedral logical group in the error correction section 7. And different logical groups gives us different tessellation, and different tessellation will be realized in different surface, ranging from sphere, Euclidean plane, and hyperbolic plane. And the fourth row of this table is the logical operators, where the right-hand side is the logical operator, the left-hand side is the corresponding geometric rotation, and we can see that they can all be realized by rotation RA, RB, and RC. And the fifth sign denotes the generalized stabilizer, means those extra relation that we impose on a proper triangle group. The last point is the resolution dx. The resolution is related to the error correction property of those tessellation codes I will discuss in following slides. But overall, different tessellations can yield different codes with different fault-tolerant logical gates. So maybe, yeah. And this is about the quantum error correction property. And we have two kinds of error in this case, which is position error and momentum error, like GKP codes. The position errors are orientation-preserving isometric transformation on a plane. And physically, it means the imprecision of implementing logical rotations, or unexpected vibration acting on the surface. And the resolution dx take care of correcting those errors, which is half of the minimum distance among pairs of adjacent points, which is similar to the resolution of GKP code, where the dx is half of the distance between two adjacent delta functions. And aside from position error, we also have momentum error. And momentum errors are eigenfunctions of the Laplacian operators on the surface. And physically, it means the kinetic energies of the modes, and also unexpected energy excitation of the physical system. And mathematically, they are basis of irreducible representation of the isometry group. And we did some estimation based on Schur lemma, and it turns out that for most of the momentum error, the quantum error correction condition is satisfied for our code. Here is the summary and outlook. And in this work, we introduce a geometric formalism for constructing continuous variable quantum error correcting code whose designated logical gate sets can be realized by geometric rotations. And its error correction property are tightly related to geometric properties. And we observed interesting interplay between lattice symmetry, geometry, and error correction, and easily implementable logical gate sets. And there are a few future directions. And the first point is that the error correction protocol for momentum error And second point is that for our code word and hyperbolic plane, it is infinite superposition of delta functions, means the code word is unnormalizable. And to make it more physically relevant, it will be interesting to see the regularized version of the code word with approximate logical gates. And the third point is that it would be interesting to see whether it's an analog of the Easton-Kneel theorem in this geometric setting. And last point is that recently there are some studies about the GKP and magic, and it may have something to say about the geometric interpretation of the magic gates or magic states, continuous variable magic states. Yeah, and thank you.
Any questions?
Thank you for an excellent talk. Do you think this approach to creating error-correcting codes lends itself to creating error-correcting codes for oscillators encoded into oscillators as well?
Yes, because in the original paper by Dennis and Deverier, there's no constraint on the logical Hilbert space or physical Hilbert space. Although here we are interested in the logical space, which is discrete variable, but it is possible to do for logical Hilbert space, which is continuous variable.
Okay, thank you.
Any other questions? Okay, let's end.
So it seems like Victor raised his hand, but
How are these related to GKP code?
so for the Euclidean plane case, for the Euclidean plane case that I presented, it can be regarded as a GKP code where we encode the logical qubit into two physical modes. Because we are interested in 2D, our physical Hilbert space is a 2D real space. So instead of the phase space of the regular GKP code, it is a GKP code where we encode the logical qubit into two physical modes. And although the logical gates I presented can be implemented by rotation, but they can be also implemented by displacement in this case.
Okay, let's thank Yixu again.